This is part 2 of our lesson on proving trigonometric identities. So let's continue with some more difficult ones. So our next one, we've got two fractions, 1 over 1 minus sine minus 1 over 1 plus sine x is equal to 2 tan x over cos x. So we can really start with any one here. So I'm just taking a look at this one, and I notice that we've got two fractions that can be combined. So we can make common denominators and subtract the numerators. Also, in our on our right side here, we have a tan x that we could substitute for sine x over cos x. So whichever one you want to start with, go for it. So let's just start with the left side. So we have our left side is equal to 1 over 1 minus sine x minus 1 over 1 plus sine x. So if we were to make a lowest common denominator, the lowest common denominator would be a combination of these two things. So 1 minus sine x times 1 plus sine x. So that means I would have to multiply this fraction by 1 plus sine x, same within the denominator, 1 plus sine x, and the other fraction by 1 minus sine x. So this guy gets multiplied by 1 minus sine x and 1 minus sine x. So what would result is we'd have a numerator. Our numerators, we would be subtracting them. So our first numerator is 1 plus sine x. Our second numerator, we'd be subtracting it, is going to be 1 minus sine x. And all I'm doing to get that is just distributing the 1 inside the bracket. We've got a 1 inside the bracket here. We've got a negative in between. And our new denominator is going to be 1 minus sine x times 1 plus sine x. So let's keep on simplifying. The left side, in the numerator, we have 1 plus sine x, and we have minus 1 plus sine x. I'm just distributing that negative 1 into the bracket here. And we have all over our denominator 1 minus sine x over 1 plus sine x. So in our left side now, we have 1 plus sine x minus 1 plus sine x. So those 1's minus 1's, those are going to cancel out. And we're just going to be left with 2 sine x. So when we rewrite it, we're going to have 2 sine x's all over 1 plus sine x and 1 minus sine x. So it doesn't look like we can simplify it anymore. The only thing we could do is expand the denominator, but it doesn't look like it would help us. So now let's take a look at the right side. So our right side of our equation right now is 2 tan x all over cos x. So on our left side, we don't have any tan x's. So why don't we change this tan x to sine over cos. So our right side is going to equal 2, instead of tan x, I can write sine x over cos x, all divided by cos x. And we can make this substitution since tan x is equal to sine x over cos x. Okay, continuing to simplify, we've got our right side is going to equal 2 sine x all over cos x divided by cos x, which is the same thing as multiplying by 1 over cos. So our final step would be to multiply these two fractions. So we have 2 sine x all over cos squared x. So taking a look at the left side and the right side, they don't quite match. Our numerators are the same, 2 sine x, but our denominators aren't the same. But we know they have to be equivalent. So this looks like it's simplified as much as it can. Can we simplify this further? Well, we could expand this and see what that gives us. So if we continue writing, our left side is going to equal, in the numerator we have 2 sine x, and in the denominator, let's FOIL this. So we're going to multiply the 1's and then the 1 times negative sine x, and then sine x times 1, and sine x times negative sine x. So 1 times 1 is 1. 1 times negative sine x is negative sine x. Then we have sine x times 1 is going to be positive sine x. And then sine x times negative sine x is going to be negative sine squared x. If we continue simplifying, we have 2 sine x in the numerator. In the denominator, negative sine x plus sine x is going to cancel out. We've got 1 minus sine squared x. So is this equivalent to cos? Because if it is, then we've proven our trigonometric identity. So if we start off with the Pythagorean identity, so since Let's do it in blue. So since our sine squared x plus cos squared x is equal to 1, now isolate for cos. That implies that cos squared x is the same as 1 minus sine squared x, which means that we can replace 1 minus sine squared x with cos. So because of this, therefore, we can change our left side to 2 sine x all over cos squared x. And now our left side is equal to our right side, and we are done. Let's take a look at our next example. So we have 1 plus cotan theta all over cosecant theta is equal to sine theta plus cos theta. So at this point, you should try to work these out on your own and then come back to the video. And if you get stuck, try to use some of the strategies that I've suggested. But they're not the only way to solve these trigonometric identities or prove these trig identities. There's lots of different ways to do it. So if you're trying this on your own, if you take a look at both sides, there's nothing we can really do to sine theta plus cos theta, especially because there's no squared involved, so we can't use the Pythagorean identity. So the best bet is to start with the left side. So we have our left side is equal to 1 plus cotan theta all over cosecant theta. So our final answer has sine and cos, not cotan and cosecant. So let's rewrite these as their original reciprocal trig ratio. So 1 over tan theta is equivalent to cotan, and cosecant is equivalent to 1 over sine theta. So now in the numerator we have two fractions that we can add together. But just looking forward, we know that this is supposed to equal sine theta plus cos theta, which means there's no tan thetas in sight, which means it might make sense for us to change this tan theta right now to sine over cos. So 1 over tan theta is going to be the reciprocal of sine over cos. It's going to work out to cos over sine. That is the definition of cotan. So we have left side is going to equal 1 plus, let's change this cotan or 1 over tan to cos theta over sine theta all over 1 over sine theta. So now we can combine these two fractions and add them together by making sure that the denominators are same. So our common denominator would be sine theta. So on our left side now, we'll have 1 times sine theta, that's sine theta, plus cos theta all over the common denominator sine theta. And now we still have this divided by 1 over sine theta. Well, that's equivalent to multiplying by sine theta over 1. So if we finish this up over here, we have that our left side is going to equal sine theta plus cos theta times sine theta all over sine theta times 1. So we have two factors on the top. We have sine theta plus cos times sine, that's our second factor, and we have one factor at the bottom. So we can cancel out the sine thetas because sine of an angle divided by sine of the same angle is just going to be 1. So we have our left side is equal to sine plus cos. And if we take a look at our right side, that's what our right side equals as well. We have sine of the angle plus cos of the angle, which means our left side is equal to our right side, and we have proven this identity. So let's try a couple more examples. So at this point, when you see a new example, you should be trying it on your own first and then come back to the video if you get stuck. And remember, if you've solved it in another way, that's okay, as long as we get to the same statement that both of our sides are equivalent to each other. So taking a look at this guy, we've got our left side is 2 cos squared theta minus 1, and then our right side is cos squared theta minus sine squared theta. So these squares let us know that maybe the Pythagorean identities are going to become helpful to us here. So we can really start with either side here. Something I see is the 1, and we know that 1 is equal to cos squared theta plus sine squared theta. So I know I can replace that 1. Another thing I notice is this looks like the Pythagorean identity, but it's not. If it was a plus here, we know that'd be equivalent to 1, but there's a minus. However, I notice that this side has cos squareds, and this side only has cos, and this side has sine and cos. So if I were to replace sine with something that used cos instead, then I would get rid of the sign and just be left with cos, and maybe both sides would be equal to each other. So I'm going to try starting with the right side here. So starting with the right side, I have cos squared theta minus sine squared theta. And let's start with the Pythagorean identity. So we know that sine squared theta plus cos squared theta is equal to 1. Well, what if I want to replace my sine? So let's put a little squared here. So let's get sine by itself. So sine squared theta is equal to 1 minus cos squared theta. So that means when I'm going to replace sine squared theta with 1 minus cos squared and see what happens. So I've got my right side is going to equal, leave the cos squared alone because our left side has cos in it, minus, and now I'm going to replace sine squared theta with 1 minus cos squared theta. So our right side is going to be cos squared theta minus 1 plus cos squared theta. So this is going to simplify to cos squared theta plus cos squared theta is 2 cos squared theta. And then I have minus 1. And that happens to be exactly what my left side is. My left side is 2 cos squared theta minus 1. So therefore, our left side is equal to our right side, and we are done. So we're going to work on 2 last examples. So at this point, I strongly urge you to try these on your own, and then come back to the video when you get stuck. So taking a look at this one, our left side looks very, very similar to our right side, which means they're both sort of the same complexity, so it really doesn't matter which one we start with. We might even choose to work on them consecutively. So why don't we try that? Because they're so similar, I'm going to write our left side on this side, so 1 minus secant x, and I'm going to write our right side on our other side. So we have cos x plus 1 all over 1 plus secant x. Okay, so unfortunately we don't have a squared in our cos, so we can't use our Pythagorean identity. However, we know that we can change secant to its reciprocal function, which is going to be cos. So we can rewrite secant as 1 over cos. This is going to be cos x minus 1 all over 1 minus 1 over cos x. And let's do the same on the other side. So on our right side we have cos x plus 1 all over. Let's change that secant x to 1 over cos x. Okay, so in the denominator now we can combine these 2 fractions. So we've just got to make like denominators. So in the denominator I have 1. I'm going to multiply this guy by cos x and this guy by cos x. I'm going to do the same thing to this guy here. This is going to be over 1. The denominators are going to be cos x times cos x. And our left side is going to be equal to cos x minus 1 all over. In our denominator, I'm going to have cos x minus 1 all over the common denominator cos x. So I have cos x minus 1 all over the denominator of cos x. And on our right side, we have something very similar. In our numerator, we have cos x plus 1. And our denominator is going to simplify to cos x plus 1 all over cos x. So we can see that this patterns emerge where we have the numerator is copied in the denominator, same with here. So we have it listed twice, which could work out really well for us. So let's take this denominator here, and instead of writing it divided by this, let's change it to multiplied by this reciprocal. So this is equivalent of saying the left side is equal to cos x minus 1, all multiplied by the reciprocal of what's in the denominator right now. So multiplied by cos x divided by cos x minus 1. And then we can write the same thing on the right side. We can rewrite this as the numerator cos x plus 1 and then multiplied by the reciprocal of the denominator. So times cos x over cos x plus 1. So we can see that the numerator is factored. Our factors are cos x minus 1 and cos x. And our denominators are factored. Our factors are 1 and cos x minus 1. Same with our right side here. So because it's all factored, we can cross these out because cos x minus 1 divided by cos x minus 1 is going to be 1. And on our right side, we have cos x plus 1 divided by cos x plus 1 is also going to be 1. So to finish this off, on the left side, we're going to be left with cos x, and on the right side, we're going to be left with cos x. And so therefore, our left side is equal to our right side, and we've proven this identity to be true. All right, we've made it to our last example. So take a look at this, try it on your own, come back to the video if you need any strategies. So taking a look at our left side, we have 2 over cos squared theta. So because we have that cos squared theta, maybe we can use the Pythagorean identity. On the right side, we have 2 fractions, 1 over 1 plus sine x and 1 over 1 minus sine x. I know that if I have fractions, I can combine them by creating a like denominator. So why don't I start with this guy here, because I know I can combine those 2 fractions. So I'm going to start with the right side this time. And our right side is equal to 1 over 1 plus sine x plus 1 over 1 minus sine x. So if I were to make a lowest common denominator, that would be a combination of both of them. It would be 1 plus sine x times 1 minus sine x. So my first fraction, I've got to multiply it by 1 minus sine x. And I'll do the same thing, the denominator times 1 minus sine x. And in my second fraction, I've got to multiply by 1 plus sine x, as well as in the denominator 1 plus sine x. Okay, so now my numerator, my first numerator is going to read 1 minus sine x. All I'm doing is I'm distributing this 1 inside the brackets. And then I have plus 1 plus sine x. All over the denominator 1 plus sine x and 1 minus sine x. So now to simplify the numerator, I'm going to have 1 minus sine x plus 1 plus sine x. So minus sine x plus sine x, those are going to cancel out. And I'm just going to be left with 1 plus 1. So my right side is going to equal 1 plus 1. And my denominator is going to equal 1 plus sine x and 1 minus sine x. So I know 1 plus 1 is going to simplify to 2, which is exactly what I need. My denominator should equal cos squared theta, but it doesn't look like that right now. So instead, I'm just going to erase this, and why don't I expand? So I'm going to expand the current denominator, 1 plus sine x times 1 minus sine x. So when I expand, I have 1 times 1, this is going to make 1. 1 times negative sine x, that's going to make negative sine x. And then sine x times 1 is going to be plus sine x. And then sine x times negative sine x is going to be negative sine squared x. So simplifying, I've got 2 all over. And then I've got 1 minus sine x plus sine x. So these sine x's are going to cancel. And I have 1 minus sine squared x. And I know I can substitute 1 minus sine squared x because of the Pythagorean identity. So since sine squared x plus cos squared x is equal to 1, well then cos squared x is equal to 1 minus sine squared x. So that means I can replace 1 minus sine squared x with cos squared x. So I have my right side is going to equal 2 over 1 minus sine squared x, which is cos squared x. My left side, now just taking a look at that, is already 2 over cos squared x, or theta. You know what I realized? That this original question should have had an x here. So let's just change this. That was theta, and this should be x. Okay, so our left side is equal to 2 over cos squared x. And I have proven that left side is equal to right side, so we are done.